Hello, everyone. Welcome all of you to this tutorial on the causal inference and the stable learning. I'm Peng from Tsinghua University, and I will deliver the tutorial together with Zheyan and Shen, senior students in my group. In this tutorial, we will introduce why the machine learning, they need the causal inference, and how can we apply the causal inference techniques into the learning framework to help to solve the stability problem of today's machine learning, okay? So machine learning techniques actually are impacting our daily life. Just from your wake up from the morning to the night, actually you will experience a lot of AI technologies, right? Like GPS, like a recommendation system, searching system, and most of them are actually based on the internet platform. And in this kind of applications, actually there is a feature that all of them are performance driven. So here I say performance driven means that we only care about the performance like accuracy. When you just can increase the accuracy by 1%, then you can increase your revenue by 1%, right? Something like that. But actually, we rarely think about the risk about this kind of predictive models. So for example, if the system recommend a wrong movie to you, right? You just watch it for 2 or 3 minutes and then you realize, okay, this is not I like, okay? So actually there is no big deal, right? So in this kind of applications, we just need to be performance driven and you don't need to care about the risk. There is no big deal, right? But in recent years, actually, there is a trend that the AI technology try to step into some risk-sensitive areas, such as the healthcare, the law, and the transportation, and also the fintech. And all of these areas are high-stake areas. That means when the AI system, they made a mistake, then this will be a big mistake, right? For example, in the healthcare, the mistake may cause a life problem, right? And in the law, if the system, they have a systematic bias, this is something related to social justice, right? And in fintech, if the AI system made a mistake, it's still a money problem, but this is a big money problem, right? So in this kind of areas, actually, we need to shift from the performance-driven paradigm to some risk-sensitive paradigm. We must care about we must be very careful about the potential risks of today's machine learning models and AI technologies, right? So then let's try to see some problems of today's machine learning and AI. I think a very notable problem is just the explainability problem, right? Because most of the machine learning models are just black box models, right? We feed into the data and also the supervised information, and then the model will just tune the parameters in a way like a black box, okay? So this kind of model, they can predict, okay, whether there is a certain kind of disease in this picture. But if you ask why, you just tell there is such a kind of disease, and if you just want to know why this is not another kind of disease, and when I should trust and when I can't trust you, something like that, some questions like that, okay, that the computer, the model cannot give you the answer, right? Okay, so of course, explainable is quite important for people to adopt this kind of knowledge, technology. But I want to emphasize that in some high-stake areas like health, military, finance, and the industry, and so on and so forth, in this kind of high-stake areas, actually, we cannot purely rely on an AI system to make decisions, right? So the ultimate paradigm should be human in the loop. That means the human should work together with the AI algorithm to make the final decision. But a very important precondition for the human in the loop pattern actually is the algorithm and the human, they should have some common language. This is a common ground for them to work together, right? So if the algorithms are unexplainable to human, then they cannot work together to collaboratively make the decision, right? I think this is a quite big challenge for today's AI technology to be applied into this kind of high-stake areas, okay? So this is explainability problem. And the other very serious problem of today's machine learning is just the stability. So we know that most of the machine learning methods are actually developed under a very basic hypothesis, that is IID, right? We just assume all of the samples, they are selected or they are drawn from an independent and identical distribution, okay? So that means if I train a model in this kind of training distribution, actually the model require you can just apply this model in the same distribution, tested distribution, okay? So that means we ask the test data to be similar or in the same as the training data, okay? So this is actually quite infeasible in the real applications, right? But today's model, if you just apply the model into another kind of distribution like this, actually there is no guarantee in both practical use and also in the theoretical guarantee, right? So this is actually is very dangerous. That means, okay, you train a model, we apply this kind of model in real applications, then you need to know, okay, what kind of distribution you can work and what kind of distribution you can't work. But actually, when we use a model, actually we don't even know what kind of data was used to train this kind of model, this model, right? So this is actually a very unrealistic assumption hypothesis for the real applications. So that means when today's model, when you just use it in real applications, there will be serious stability problems. Okay, here I will just show you two very simple examples. One is just for the image classification. So here is quite a simple task. I just want to build up a dog classifier, okay? So this is the training data. And from the training data, you can observe, for these are some samples, for example, randomly sampled from the training data set. And here you can see, observe some features, right? Most of these dogs are actually on the grass background, right? And some of them are not, but just a minority, okay? So with this kind of training data, we train a model for the dog classifier, okay? And then if I test the model using this kind of case, maybe the precision will be above 90% or even 95%. I mean the precision, right? So this is what today's deep learning is really good at, this kind of case. So if I give this kind of test case, maybe sometimes it's correct, sometimes it's wrong. Maybe the precision is just around 70%, okay? But if I give you this kind of test case and just throw the dog into the water, actually the model can never tell this is a dog. Okay, the precision should be maybe below 20% or 30%. So why? Because this kind of feature distribution, the data actually is far from the training distribution. Okay, so that means when you train a model, you apply it into different environments, actually the stability is really a very serious issue, okay? So here I'll just show you another example, non-visual, but the feature-based data scenario, okay? So I just want to build up a cancer survival rate prediction model. For example, the training data, most of the training data, they are collected from the city hospital, okay? So in this kind of training data, actually you will observe a very strong correlation between the income and the survival rate. So actually it's quite easy to understand, right? If you can pay more money, you will get better treatment, right? And then you will have a higher survival rate. So it is quite easy to understand, right? So this is actually a very strong correlation pattern. And if you build up a survival rate prediction model, then the income will be a very strong factor for the prediction. Okay, so if I just apply this predictive model into city hospital data, testing data, then this is actually follow the RID hypothesis, right? And there is no problem. But if you apply this model into the university hospital data, okay, then the model will make very, very bad predictions. So why? Because in the university hospital, the level of treatment that you can get is not determined by the money you pay, but it's determined by research purpose, right? So in this kind of scenario, you can see, okay, they will make big mistakes if you just change the data distribution and also the environments, okay? So we just want to analyze, so what is intrinsic reason? So why today's model is not explainable and also is not stable? So here we just want to say that a plausible reason maybe is the correlation. You know that today's machine learning correlation is very basic of a statistic unit, right? But the correlation actually is not that reliable. So especially in big data environments, every two trending variables, actually they are correlated. So here you can see this is a joke. This is just an example of correlation. So in this company, they just observe that, okay, this is a sales volume, right? And this is a number of shaved heads in this company. You will see that they are just strongly correlated, right? So then the boss just say, hey, let's just take a reason to increase the sales volume. Okay. Of course, this is quite ridiculous. So why it's ridiculous is just that the correlation actually is not very reliable, right? And here we want to say that with respect to the explainability and also stability problem, we can see that correlation itself as a basic unit of machine learning, today's machine learning itself is not explainable. So here I just show you this case. Actually, you can see these two curves are very correlated, right? And the right curve means the people who joined after falling out of a fishing boat, okay? And the other curve is just the marriage rate in the Kentucky, right? They are just strongly correlated, but you can just hardly to interpret one variable with the other variable, right? So that means, okay, correlation itself is not quite explainable. And also correlation is not stable, right? In this example, actually, when the training data is this kind of distribution, you will the machine, the model, they will discover both the red features and also the yellow box features. They are highly correlated with label of dog, right? So why? Because all of the most of the dogs, they're on the grass. So the model will treat just identify strong correlations between the grass features with the label of a dog, right? But this kind of in today's model, they will exploit both the red features and also the yellow box features to make the predictions. But when the environment change, when most of the dogs, they're not on the grass, but at home or on the beach or in the cage, okay, the model will make serious mistakes, right? So if you can just try to differentiate this kind of causal, the red features and the yellow features, and we depend on the yellow features, to do the predictions, maybe the stability problem can be solved, right? Okay, from the previous analysis, maybe we want to blame the correlation, right? It's not reliable. But I want to say that it's not the fault of the correlation, but the way we use it in the machine learning models. Actually, there are three sources to generate correlation. So one way is just the causation. For example, if T cause Y, then we will observe a strong correlation between T and Y, right? For example, each summer, the summer temperature is high, and then the ice cream sales will increase, right? So we will observe a strong correlation between the summer and ice cream sales, right? So in this kind of correlation, actually is stable and also is quite easy to be explained, right? Okay, so this is one way. The other way actually is generated by confounding. So the confounding means that the X cause T and also the X cause Y. Okay, because T and Y is simultaneously caused by X, so we will observe a correlation between T and Y. Okay, so here we just show you quite a real example in the recommendation system in China. So the recommendation system often recommend bars to the pregnant woman. Of course, we know that this is ridiculous, right? But if you just try to find out the pregnant woman, the correlation between the pregnant woman and also the bar, they are indeed highly correlated from the statistical correlation view. Okay, so why they just generate this kind of correlation? Actually, because they are simultaneously caused by a latent variable that is age. Okay, because the age in some period of age, okay, the woman will be pregnant, and also in a certain period of age, the woman tend to go to bar more often. So you will find out, okay, in the same period of age, okay, the pregnant and the bar, they will have very strong correlation. But I would say this kind of correlation actually is quite spurious, right? And it's not stable, and also it's not explainable, right? So this is a confounding. And the third way to generate correlation is by sample selection bias. Okay, just like the example I just showed in the dog classification problem. So we just tend to select this kind of dogs on the grass. So this kind of selection bias actually will induce the correlation, spurious correlation between the grass and the dog. And this kind of correlation is also spurious correlation, and they are not stable and they're not explainable, right? So here you can see that we have three sources of correlation, but only the first one actually is stable and explainable. But in today's machine learning models, actually, we just use all of these kinds of correlation for prediction. And we don't even try to differentiate different kinds of correlations. We think this is actually the intrinsic reason of causing the stability problem and also the explainability problem of today's machine learning models. Okay, so just now we mentioned the concept of the causality. So here we just give you a quite easy and a practical definition on causality. So here the definition is that T, if we say T causes Y, if and only if changing T leads to changing of Y while keeping everything else, that means the X constant. Okay, if I just keep X is constant and I change T, then Y change. Okay, the only way we can interpret is that Y's change is caused by T, because all of other things, they are not changed. right? Okay, so this is actually the quite simple definition of the causality. Okay, so if we can frame it in this way, then we can define the causal effect. Okay, so the causal effect is just the magnitude by which y is changed by a unit change in t. Okay, so this is actually the causal effect of t on y. So this is actually called the interventionist interpretation of causality. Okay, so if we can identify this kind of causality from the data, then what's the benefit of bringing this kind of causality into learning? So here I just show you the example of the dog classification. So if I just, for example, the t is a grass. The t actually usually called the treatment variable in the causal literature, and the x that the dog knows, and the x is called the confounders, and the y is the label, right? Dog label. Okay, so in the causal literature, if I treat t grass is a treat. One group, they have the grass, and but both of these two groups, they have same distribution on X. That means, for example, both of these two groups, they have dog nose. Okay, but one group, they have grass, and the one group, they don't have the grass. Okay, then you can see the difference on the Y, the label distribution in the two groups. Because these two groups, they intuitively, both groups, they have the dog nose, but only one has a grass and one don't have the grass. Actually, their label distribution will be similar because we know by ground truth that they are actually, both of these two groups are dog pictures, right? So actually, you can guess that the T, the ground effect on the Y. Okay, so if we just reverse this T and X, we use the dog nose as a treatment, and we use the grass as a confounders. That means we form two groups. One group, they have the dog nose, and one they don't have the dog nose. But both of them, they have the grass. Okay, you can imagine that, okay, these two groups, they will have different label distributions, right? The one group, the group with the dog nose, they are more possible to be labeled as dogs, and the groups they don't have the dog nose, they will have lower probability to be labeled as dogs, right? Then we will find out, okay, the dog nose actually they have the treatment effect or causal effect on the Y, right? So if you are just using the causal framework to interpret the data, you will find out, okay, the grass and the label, they are strongly correlated, but there are weak causation between these two variables. Okay, but if you evaluate the dog nose and the label, they are also strongly correlated, and at the same time, they have strong causation. Okay, so then this tells us that, okay, the grass cannot actually, it's better to not use this kind of features to interpret and to predict the kind of causal features like the dog nose, dog eyes, and dog ears. And using this kind of features to make predictions, then the predictive model will be more explainable and also more stable, right? Okay, so the causality, the causal inference literature and the learning literature, actually there are still a large gap between these two communities. So first one is for the causal inference, actually there are some tough problem that actually quite difficult to solve, is how to evaluate the outcome. How can you know the ground truth of the causal relationships, right? So this is actually quite challenging problem for the causal inference. And but for the learning, actually, we need to do some quantitative evaluation on the prediction results, right? So there are some gaps in this sense. And the second one is in the causal literature, causality, causal inference literature, most of the models actually they are developed and also evaluated in some clean or well-controlled environments, right? But in the learning, actually we need to confront the wild environments. So here the wild environments featured by the very high dimensional representation space. That means you may have thousands or tens of thousands of variables in the system. And also this variables are highly noisy. Okay, there are a lot of noise that you don't have any prior information in the data. And also we have little prior knowledge about the causal structure, right? In the causal inference, of course, you can exploit the expert knowledge to identify or they provide the basic causal structures. But in the learning problems, for example, the image classification problem, we have tens of thousands of concepts that need to be categorized. We cannot provide sufficient prior knowledge to define this kind of causal structure, right? So how can we apply the traditional causal inference techniques into the learning environments? Actually, this is also quite challenging, a big gap. And the third one is actually these two line of research, they have different targeting problems. So for the causal inference, actually, they are more for understanding the data, for pre-description, right? And for the learning, actually, we mainly focus on prediction problems. So this is actually quite different. And also for the causal inference, we care about, okay, how deep we can understand the data. But in the learning, we care more about how can we scale up, right? How can we scale up the model into billions of data samples? And also we care about the prediction performance. Okay, so here you can see that both of these two directions, actually they have quite substantial difference. So how to bridge the gap between the causality and the learning? Actually, this is the purpose, real purpose of this tutorial to explore. Then I will just briefly introduce the literature of causal inference. In the causal inference, there are two major paradigms. One is a structured causal model that is by the UDPro. Actually, this is a graphic model to describe the causal mechanisms of a system. So for a system, you have a number of variables, and the graphical model actually can tell the dependencies, the causal dependencies among these variables, who cause whom, right? And when you get this kind of a structured causal model, then there are some complete theory to support us to do the, for example, the causal identification with the backdoor criterion, and also you can do causal estimation with do calculus, right? So the most challenging problem is how to discover the causal structure, okay? In some application scenarios, of course, we can ask the domain experts to manually define the causal structure. But as I said, a lot of domains and application scenarios actually is quite difficult, quite challenging to get this kind of causal structure, right? Then there are some research on the causal discovery. In the causal discovery, actually, just so we want to use some automated method to do the conditional independence testing. Okay, we just to test whether these two variables are independent and whether they are independent given some variables. And with this kind of independence testing, actually, we can come out the final causal graph structure. Okay, but of course, as I just said, when you have many variables, this is actually a combinatorial problem, right? So the complexity is often unfoldable for real applications, especially for large-scale data, for large-scale learning problems, okay? So I say that structured causal model is a generative model with very strong expressive power, but it induces quite high complexity. So this is actually the, I think is biggest limitation of this kind of framework in the real applications. And the second paradigm is potential outcome framework. Make it computational, efficient, and to make it affordable, make it feasible. Actually, they make a simpler setting. And just suppose that, okay, the objective is just to evaluate the causal effect of one variable to the outcome. Okay, so comparatively, in the structured causal model, we want to figure out all of the causal relationships among all of the variables, right? But here, we just potential outcome framework just want to evaluate the causal effect, the treatment effect of one variable to the outcome variable, okay? And in this framework, they make a strong hypothesis that they suppose that the confounders of T are known a priori. Okay, so when this hypothesis is satisfied, okay, we can evaluate the treatment effect in a correct way. Okay, so the computational complexity of potential outcome framework is affordable. It's under the stronger assumptions that all of the confounders, for example, that all of the confounders need to be observed. Actually, this is also a limitation of this kind of framework. I think this is more like a discriminative way to estimate the treatment's partial effect on the outcome, right? So we can see that this two framework is quite different. Because for the learning, we care more about the scalability problem and also the performance. So in the later discussion, we will mainly focus on the potential outcome framework. Okay. So in this framework, let's define the causal effect estimation problem. So here there are some basic concepts. One is a treatment variable. Okay, the treatment variable here. T1 means that it's treated, and T equals to 0 means the sample is not treated, is controlled. Okay. Then we will form two groups: the treated group and the control group. Okay. So then for these two groups, they will have some potential outcome. That means for the treated group, you have an outcome. In the control group, you have another outcome, right? And then the average causal effect, and also called average treatment effect, the ATE, can be calculated by quite simply, right? Just the expectation of YT1 minus YT0. Okay, so let's just take a quite intuitive example in the medicine. For example, you just want to evaluate whether a medicine is effective for a kind of disease. Okay, then the medicine, the drug, is just the treatment. Okay, and the X, the confounders, actually they are the, for example, the characteristics, their features of this patients, candidates. Okay, so we just can form two groups. One is a treated group, and one is a control group. For the treated group, we can just give them the pill, the medicine. But for the control group, we just give them the placebo, right? And we ask that these two groups, they will have similar distributions on the X, okay? Similar distribution on X. Then if these two groups, they have different outcome, then the different outcome can only be caused by the medicine, right? Because all of the other confounders, they're controlled, they're the same, right? then we can say that, okay, the medicine is effective to the disease, right? So this is actually the average causal effect, the ATE. But the challenge is in the real case, actually, we must face the counterfactual problem. That means for each patient candidate, you can only take the medicine or take the placebo. You can never take, for example, both the medicine and and the placebo, right? That means for one candidate, we can only know the YT1 or YT0. We cannot know both simultaneously, right? Okay, so someone may say that, okay, this time I got this disease, I take the medicine, and next time I get this disease, I just take the placebo, and then I can compare, right? No. Why? Because you must keep everything else constant. Two times, just as the same patient candidate, in two times, their body, for example, their body condition can be different, right? So there was a saying that you cannot step into the same river twice, right? So this is actually the counterfactual problem. This is a counterfactual problem. So this is quite challenging, and the most challenging problem, fundamental problem in the causal inference, okay? So the ideal solution is just whether we can reason about a counterfactual world. So everything in the counterfactual world is the same as the real world, except the treatment, okay? So of course, this kind of counterfactual world cannot exist in the real world, right? But whether we can reason about such a counterfactual world, right? So this is actually the intrinsic way to solve the counterfactual problem. Okay, so a gold standard for this kind of counterfactual problem is just to do some randomized experiments. Okay, I have a pool of patient candidates, then I will just randomly split them into two groups. Because I do random splitting, so there will be no bias on the X distribution, on the confounder distribution of these two groups, right? And in this way, of course, we can guarantee this, in these two groups, they have the same X distribution, but just one group, we gave them the medicine, and the other group, we gave them the placebo, right? So this is actually the golden standard that has been widely adopted in a lot of application scenarios. But the drawbacks of this kind of randomized experiments is that, okay, there will be very high cost because you need to recruit a lot of candidates, right? You need to pay for this kind of, pay much for this kind of experiments. And the more serious problem is that a lot of problems, actually, you cannot do this kind of random experiments because there may be unethical. For example, you just want to identify the causal effect of smoking to the lung cancer. So you just recruit a lot of volunteers and randomly split them into two groups and ask one group to smoke and ask another group not to smoke. Of course, this is unethical, right? You cannot do that, okay? So this kind of golden standard is not very realistic in many application problems. So in recent years, actually, there are a lot of research that is on whether we can just do this kind of causal inference and the causal effect estimation from the observational studies and from the observational data. So this is a right way to go to solve this kind of problem. Okay. So causal inference with observational data actually is a quite important problem. So here the counterfactual problem, we know that it's just a YT1 and a YT0. So a very straightforward solution is that whether we can for example, you have big data environments, you have a lot of samples, and I just selected the treated samples and the controlled samples, and then I directly use them to estimate the ATE, to comparing their average outcome between these two groups. I'll say we cannot do that. So we can do that with randomized experiments, because you just randomize X. We can guarantee that in these two groups, their X are the same in the randomized experiments, but in the observational data might be different. So you cannot directly formula to calculate their treatment effect. Okay, so here actually the problem is on the confounding effect. So what is a confounding effect? So here you can see that maybe if you just directly to form the treated and the control group, for example, a group of persons, they smoke, and another group, they don't smoke, then you will get the conclusion that, okay, the smoking can increase your weights, because you just directly calculate their ATE, their outcome. There are substantial or significant differences between these two groups. But if you take the age as a confounder, you find out, okay, actually the weight increase is not caused by smoking, but caused by the age. So they're correlated, and there are some substantial difference in these two groups, because when your age grows, you tend to smoking, maybe because you have more things to worry about, okay? And when your age increase, when you grow up, then you will take less sports, and your weight will just increase, okay? So that means the age actually simultaneously cause the treatment, the smoking, and also the weight. So if you don't try to balance this kind of confounder, I mean the age distribution, you will just get some wrong conclusions, right? The intrinsic challenging problem is how to balance the confounders distribution. So in order to solve this problem, there are different lines of research. One is on the matching, the sample matching. So pool data candidate samples. Then these are the treated samples, and these are the treated samples, and these are the control samples. Then I can just directly do some matching, right? Just for example, this sample, treated sample, they have the same X, same confounders with this control sample. Then this will form a matched pair, right? And then I will just try to find out all of the matched pairs, okay? Group and their X are just the same. And then I form the treated group and the control group. Then this matching process will guarantee, okay, these two groups, they will have the same X distribution, right? And if a sample cannot group, then this sample will just be discarded. Okay, so this is a matching process. Of course, you can define, for example, a distance metric to measure the X similarity or their distance, and you set up a threshold. And if this two samples, okay, their distance, their confounder distance is smaller than this threshold, you just form a matched pair, right? And the smaller epsilon, the smaller threshold, of course, they will result in less bias, right? Because the matching will be more accurate. But this will result in less matched pairs, and the less matched pairs will induce higher inference in the estimation process, right? So this kind of matching for things, but in high-dimensional setting, will be quite few exact matches. Okay, so this is a major problem of this kind of technology. Then later on, there are some methods to lose this kind of assumption and propose the propensity score. The propensity score actually, the EX is represent the probability of a unit to get treated. Okay, just in this formulation. Okay, just for example, the probability for a patient to take a certain kind of medicine. Okay, so this is actually the propensity score. And Donald Rubin actually theoretically shows that the propensity score actually is sufficient to control or summarize the information of confounders. That means if you can calculate the propensity score correctly, then the control same as the absolute matching methods. Problem is propensity score cannot be observed, right? You need to estimate the propensity score for each data sample. Okay. Then the problem is how can we estimate? So in our data, we have, for example, given a data sample we have is X, and also we have whether this is treated or control, right? So we can just transform this propensity score estimation problem into a supervised learning problem. You just predict a known label T based on the observed covariance X, right? Okay, if this model, if this supervised learning model actually you have correct model misspecification, you have sufficient training samples of the estimated propensity score, right? And you can just use a propensity score to calculate the distance between any two samples, okay, and conduct the matching. And in this, you just recall that in the absolute matching, actually, you are comparing two high-dimensional vectors, but in the propensity score matching, you just need to compare two values. Okay, so this solution actually is more fit for the high-dimensional challenge, right? But actually, this is a hard solution, still a hard solution. That means when two samples they're matched, in the sense of in terms of the propensity score, then they're maintained. But if they're not matched, okay, their distance just surpass the threshold. So this is actually not a very effective way to exploit all of the data samples. So then later, just propose the inverse of propensity weighting. This is actually a soft solution. That means we don't discard the data samples. We just assign different weights to different samples. Okay. So why we can just weighting with inverse of propensity score? Because propensity score actually induces the distribution bias on the confounder X. So here we just show you the example. So in a data set, we have three kinds of unit. So A and B and C. Okay, so this is three kinds of unit. Okay, this their propensity score, the EX, are point. Then we have 10 of A. Okay, then you can calculate that. Okay, you will get in the treated group you have 7A, 30B, and 8C, right? But in the control group you have 3A, 20B, and 32C. Okay. Of course, you can see that these two groups they are not balanced, right? just in the with respect to the unit categories. Okay, but if you just use the propensity inverse propensity score to reweight this samples, just using the propensity score is defined in this way. After you calculate the weights in this way and assign these weights to different samples, you will get, okay, the treated group, they have 10A, okay? In the treated group and the control group, their number of B and C are absolutely the same, okay? So after this kind of inverse of propensity weighting, we can just successfully to balance their distributions and to remove the distribution bias induced by the propensity score. Okay, so this is the IPW method. But the IPW methods actually they still have some limitation, because they at least they require when we just estimate the propensity score, okay, they require we have the correct model misspecification. Of course, we know that we don't have sufficient prior to guarantee the correctness of the model specification in real. Because the propensity score is formulated in this way. So when the propensity score is close to 0 and 1, the sample weights will be very high variance. Okay, and the high variance on the weights of this on the sample weights actually will significantly reduce down the effective sample size and also make the estimation model to induce very high variance, right? So this is a limitation of the IPW. So as I just said, the model specification problem actually is inevitable, right? So then can we directly learn the sample weights that can balance the confounder distributions between the treated and the control group, and don't rely on the specified model structure and calculate the propensity score, right? We can just using a quite a more non-parametric way to solve this kind of model misspecification problem. So then there comes the third branch, just the directly confounder balancing. So the directly confounder balancing, the motivation is the collection of all the moments of variables actually uniquely determine their distributions. Okay, so whether we can just directly learn the sample weights by directly balancing confounders moments, for example, just the first order moments, right? Okay, so this is the XC, that means the control group, the X matrix, and in the treated group, in the X matrix. And then we can just apply some sample reweighting or sample weights to the control group, the samples, to the controlled samples, and to ask, okay, their first order moments of the X in these two groups, they are just approximated, okay, to minimize their differences in the sense of, in terms of the first order moments. Okay, so the W actually is our optimization objective, right? We just try to directly learn the sample weights to minimize their difference. Okay, so with this kind of moments, the sample weights can be learned without any model specification. But the problem is, if you don't have any constraint on the sample weights, there will be still very large sample weights with some samples, right? And for other samples, maybe the weight will be very low. So there will be a very high variance among the sample weights. So here the entropy balancing is just to impose a constraint on the entropy of the weight matrix, so that, okay, the sample weights will be, their variance is reduced down, right? So this actually the basic idea of this entropy balancing. But this, no matter the directly confounder balancing and also the entropy balancing, both of them, they either know the confounders a priori or they regard all the variables are confounders. Okay, and all of these confounders, they are balanced equally. That means they think that the confounding bias induced by every confounders are actually the same. Actually, we think that this is maybe not a reasonable hypothesis. So the idea is maybe different confounders, they make different confounding bias, right? So we think that we need to set another weight to the confounder weights. That means we want to simultaneously learn the confounder weights beta here and also the sample weights W here to balance this two distributions. Okay, so here the confounder weights, they determine which variable is confounder. For example, if you learn the weight of a confounder to be 0, that means okay, this variable shouldn't be regarded as a confounder, right? So the confounder weights, they can determine which variable is confounder, and also it can determine its contribution on the confounding bias, right? And the sample weights here are used to for the confounder balancing, right? So of course the challenge is how can we automatically learn both the confounder weights and the sample weights from the data. And I will just skip the detail. You can refer to our paper in the KDD 2017. Now, all of these causal inference methods, actually, they have 3 assumptions. The first is a stable unit treatment value assumption that is called SUTV. Okay, that means the effect of the treatment on a unit is independent of the treatment assignment of other units. Actually, that means there is no feedback. Whether I take a medicine will not influence your decision on taking the medicine, right? There is no effect samples. And the second assumption is independent of potential outcome given the observed variables. Actually, this means that there is no unmeasured confounders. Also, this means that all of the confounders are actually observed in your data. Okay, so this is a quite strong assumption. And the third one is the overlap. That means each unit has non-zero probability to receive either treatment status when given the observed variables. And this assumption actually poses quite high requirements on the effective sample size. So these are the basic assumptions of the causal inference. And these assumptions actually are also indicates the limitation of today's causal inference methods. So now I want of previous content. In 2016, actually, there was a seminar on that was organized by the National Academy of Science in the U.S. And the topic is drawing causal inference from big data. So in the recent years, actually, there are very fast development and also substantial progress in drawing causality from big data. And in more details, most of them are trying to solve the problem, for example, from single treatment to group treatment, from binary treatment to continuous treatment, and to dealing with unobserved confounders, and also try to weaken the assumptions of the causal inferences. So there has been quite a rich body of research literature in recent years to address the big data challenge problems in the causal inference. But whether this techniques has been ready for learning, I would say that there are some a few groups they are trying to applying this latest causal inference methodologies into the machine learning framework. And I will leave this content to the second part that will be delivered by Zheyan and Shen. Okay, thank you.
My name is Zheyan, a member of research lab of Professor Peng. I will present the second part of today's tutorial, the topic about stable learning. In the previous part, which is presented by the Professor Cui, we introduced causal inference, a powerful statistical tool which could discover underlying true and also invariant structure of data under certain assumptions. Causal inference could inherently solve the instability problems of machine learning techniques. However, it also meets several big challenges in big data area where we usually encounter large-scale, high-dimensional, and noisy data. Up to now, there still exists considerable gap between these two fields. In the second part, we will first give a definition of stable learning problem, briefly review some related tasks and techniques. Then we will analyze this problem from two aspects, namely causality-oriented and learning-based, respectively. To move a bit further to real applications, we will discuss a stable learning problem on graph data. Finally, to steer the research of stable learning, we propose a benchmark named Nico for fair evaluation and a simple baseline as well for preliminary comparison. To better illustrate the idea of stable learning, we just borrowed the figure from Professor Peng, which we think the tree structure is quite a good picture to describe the relationship between the stability, computability, and also the prediction. Here you can see that the stability part actually means the true model was the true model that generated the data you observed. And for the computability, actually it corresponds to the learning process. We just try to learn a model to fit the data we got, and the prediction part just corresponds to the prediction performance. So in the traditional learning, so in the traditional learning, we are just starting from data and then try to build up a model and make some predictions. And actually, we are just doing some data fitting. Such data fitting process, actually, there is no problem only when the environment is very stable and unlikely to change. You can just imagine that there is totally no wind and the tree just stand there, which is no problem at all. If there is some moderate wind because the tree actually has no root, so it's quite easy that the tree will crash down because we don't know the true model. So if the data distribution do not change, there is no problem at all. But whenever there is some kind of wind and the data distribution change, then actually there is totally no performance guarantee here. So what we call stable learning is trying to do this. We are just trying to identify the true model from the data. We try to find out the root, and then we use the root to do prediction. That's the stable learning and the stable learning concept. We think this concept is quite different, or is a quite different way of thinking the traditional learning problem. For the stable learning problem, okay, so you just try to position the stable learning, which is different from other lines of research. Here you can see that we have training data, which is drawn from the distribution 1, and when we train a model and then we test it, and in the testing phase, actually there may be different distributions here. So if you train the model in distribution 1 and you optimize the test accuracy also in distribution 1, this is ideal learning settings, right? This is most of today's model actually do. If you just train the model from distribution 1 and you optimize the accuracy in the distribution N, this is a transfer learning setting, or more concretely, domain adaptation setting. So the precondition is, okay, you know that the test data actually is drawn from the distribution N. You have that prior knowledge. So what's the stable learning is? The stable learning is trying to minimize the variance of the accuracy in different distributions. That's the stable learning. So you can see that this is very different. We think that the stable learning actually is more realistic and more practical in real applications, because in the tree picture we just saw in the beginning, we can never guarantee there is no wind. In other words, this testing distribution is the same or similar as a training distribution, and also we cannot guarantee that the test distribution is known in advance. So how can you guarantee that the stable performance in this kind of the real setting? We think that's the problem of stable learning. So when we talk about stability, you might think about another concept, similar concepts, robustness. Robustness learning actually is quite popular in recent years, machine learning research. So we try to distinguish these two concepts. For the robustness, we think that if we focus more on the prediction performance over data perturbation, it's driven by the prediction performance. And you just think that if our data is perturbated, then how can we guarantee a robust prediction performance? That this is robustness. But in stability, we focus more on the truth model that generate this kind of observed data, and we will be more concerned with the bias, not prediction performance. We lay more emphasis on the bias between the estimated model and the true model. If we can estimate the true model correctly, we can guarantee robust prediction in different kind of distributions and in different data perturbations. So we think that stable learning is a way to realize a robust prediction, a robust learning, and maybe is a more intrinsic way to realize it. Because in robust learning, actually, we didn't have such concept of the true model. Instead, we just try to make some, for example, the adversarial examples, right? We just simulate different kind of data augmentation, perturbation that, and we learn a set of parameters that is stable in this kind of perturbated data. But in stable learning, we focus more on how to estimate a true model. So in this line, actually, there are some previous works. The first one is distributionally robust optimization. It exactly follows the idea of robustness we've mentioned above, and being formalized as a min-max problem that we are trying to optimize the worst case over a class of distributions so that the resulting model can handle some perturbations in the future, at least to some extent. Note that if the class P contains all distributions under shift intervention or dual intervention, then the causal parameter theta causal is the distributionally robust parameter. So this is the relation, actually the relationships between DRO and causal, which is discovered by recent research. Another one is the domain generalization and also inference learning scheme. In this kind of setting, you can see that there is a global distribution here, and I suppose that in the training phase, we have different environments, and each environment corresponds to a distribution, which is actually a subset of the global distribution. So this is the problem setting, and we trying to predict the outcome Y given X such that a prediction works well or is robust for all possible environments, which include the training environments and also some unseen test data. So in the domain generalization, actually, the basic assumption is that the conditional probability, the PY gamma X, is stable across different environments. If we have these kinds of assumption, we just try to take the knowledge acquired from some related domains on your related environments and then apply it to previously unseen domains. This is the key idea of the work done by Professor Shokov in his Pathfinder paper of domain generalization. They made some reasonable technical assumptions and then proved that, okay, with probability at least 1 minus delta, we can derive the upper bound of this loss. For this loss, we can see that we can approximate the potential loss by the empirical loss and add some other terms. So the difference between them is bounded by these two terms. One is the distribution of variance. Distribution of variance means that you have some unknown environments. How different are their loss? The other term actually just vanish in infinite sample size. So the problem is how can we estimate the beta so that we can reduce down the loss variance in different environments? Actually, we think this setting is more in robust learning way because actually you are just trying to find out a set of coefficients or parameters that perform robustly in different non-environments. And the problem they can solve is that if the non-distribution, their bias has been incorporated by the non-environments and non-distributions, then they can work well. But if the distribution change actually goes beyond the non-distributions, they actually cannot solve this kind of problem, which means Actually, they can do interpolation, but not extrapolation. That's the domain generalization method. And for the invariant prediction, actually, they have weaker assumption. They don't assume that the py given x is stable, but instead they suppose that there exists a subset of variables belong to x that is causal for the prediction of y, which means they think that, okay, py given s is stable across all the environments. The logic is in the input variables, there are many variables, but only part of them are the causal variable for the output. So if we just assume the causal variables or causal structures are stable and generalizable to different domains, different environments, then of course we can just use this kind of causal variables to make predictions, which can result in a stable performance. So the way to solve this problem, of course, is just trying to identify the causal variables for the outcome. And what we can do is we can resolve to, for example, the structural causal model, some other causal discovery method. If y is the outcome variable, then we can just use the parent node of y to predict it. So this actually relies on the hypothesis that, okay, you can identify the causal variable correctly and efficiently, and the causal variables are generalizable, then you can guarantee the stable predictions in different environments. First, we try to analyze the stable learning problem from a causal perspective. In the literature of causal inference, it is common to assume that the causal mechanism to be invariant across all sorts of perturbations or distribution. Thus, it is a natural way and reasonable way to leverage causal mechanism into stable learning problem. To directly apply causal inference into learning, we say that there's a variable selection way. For example, we just select a subset of causal variable from all of the input variables. Another way to do that, and which we think can be more seamlessly incorporated into a learning problem, is sample weighting. Inspired by the potential outcome framework, let's first revisit the direct confound balancing. And what we do is that given a feature t, we just assign different weights to the samples so that the samples in the treated group and the control group, they have similar distributions of input variables. That's what we did in the confound balancing. We just try to learn the sample weights. By sample weighting, we can just make a variable to be independent, and if the variable is independent, then we just need to do direct regression of y, and then the coefficients actually corresponds to the causal effect. That's the intrinsic idea of the sample weighting, but the problem is for one given t, given one variable, we need a set of sample weights to make it independent. Obviously, this is not a natural learning setting. So the problem is whether we can find a set of weight that can globally debias all of the variables. If we can find out that given any feature t, there exists the same set of weights that can make each variable to be independent, then actually we can use this kind of idea to do prediction. In the traditional prediction task, we just depend on the input variables, and we never ask the relationships between the input variables. But now if we use a sample weighting scheme, we can remove the confounding bias, and then the partial effect can be regarded as a causal effect. So the key problem is whether there exists a set of weights that can decorrelate all of these variables. Then we provide some theoretical analysis. We can prove that in the infinite sample size scenario, there do exist a set of weight W that can make the input variables in X to be independent. All of the variables can be independent by sample weights. So there exists this kind of sample weights. If we can figure out these sample weights, then we can leverage them just like the propensity score weighting, and we just regard the weighted samples at the new training data, and then we can apply every kind of learning models on this new set of data. In the learning process, we require that the learning model can incorporate different weights of these different samples. Here you can see that we can first try to learn the W from the observed data, here, x minus j represent that all of the features excluding the treatment j, and w here is apparently the sample weight, and the ij is an indicator of treatment status. When we are trying to minimize this loss, actually we're just trying to find out a set of sample weight w that can approximate that balance this treated and control group for every variable. After such global balancing, we can make them independent by this set of weights. We can naturally incorporate such causal regularizer into learning model. The difference is that in the previous learning model, we just regard each sample to be equally weighted, but now they have their own weights and differently weighted. So we can do, for example, the weighted logistic regression. And if you just do the do the traditional logistic regression, you will find the difference here. If you forget about the weighting stuff, then the beta here actually is a correlation coefficients. But if you do the weighting with which all of the variable being decorrelated, then the beta actually they imply the causal contributions not for each variable. Then we will show some preliminary results here. So this is a data set, and in this data set, we just are trying to make it easy to generate some kinds of distribution change. These images are about dogs, but we try to divide them into different contexts. For example, this is dog in the water, and this is in the car or on the grass, etc. And then in the learning process, we just use the model. But we test the model with, for example, we just use the first three contexts to train the model, but we test the model with the other two unseen contexts. By doing so, we want to validate whether a model can do a good generalization on the changing distributions. Here we will find a very interesting result so this is the result of different categories, and the bar here means the contextual bias. That means the degree of distribution change in the category between the training distribution and the testing distribution. And the curve here is the relative improvement of the causal model over the correlation-based models. So here we can see that, okay, in a category that have higher context bias, then the causal model will have larger advantage over the correlation-based models. So it is quite consistent with our previous result. We also just to try to visualize the highly weighted feature of causal model and also the correlation-based model. So you can see in the picture, the red box here are highly weighted features in a causal model, and the green box are the highly weighted features in the correlation model. We didn't do any object localization and just learn from the raw data, but finally you can find that the highly weighted features in the causal models localized within the object, mostly localized within the object region. If we want to provide an explanation of the prediction result, then I believe that this kind of causal features is more explainable than the correlation features. Theoretically, we can prove that under the law of large number and the overlap assumption we've mentioned, there exists an optimal weight W that could minimize the global balancing loss to 0, and therefore removing the confounder balancing completely, make each variable independent. In real scenarios, however, the finite sample size and high dimensional data may cause the suboptimality and high variance of learned weights. To address such limitation, we propose to leverage the power of autoencoder to map the original high-dimensional features into a low-dimensional space while capturing the underlying feature interactions. By combining the unsupervised feature representation into the global balancing stage, we can modify the original regularizer to a deep version and further propose a deep global balancing regression algorithm. Deep global balancing method could preserve the optimality of learned sample weights while making the overlap assumption easier to be satisfied. Moreover, the plug representation stage is more capable of capturing the potential nonlinear functions between input and output variables. The experimental results show that the RMSE of the deep version global balancing regression algorithm is consistently stable and small across environments under all settings. As far as we discussed, the features are constrained to be binary, as the mainstream discussions about causal inference are within the scope of binary treatment. When the treatment variable is categorical or continuous, traditional balancing methods are no longer feasible as the treatment level could be infinitely large, and in practice we could not divide such many groups. However, from the intrinsic nature of confounding bias, we know that if the treatment and confounder are independent, we could estimate the treatment effect accurately. Inspired by the independence condition for the continuous variable, we can also learn a set of sample weights so that the weighted distribution of treated and confounder could satisfy the independent condition. By doing so, we could empirically verify the uncorrelatedness of continuous input variables. In the previous part, we have discussed the stable learning from an angle of causal inference, starting from a key concept, confounding bias or global balancing. We've shown that taking the confounding bias into account during the learning process could produce models with better causal implication and therefore achieve more stable performance. So there raises a natural question that can we formulate the stable learning as a pure statistical learning problem and solve it from the learning end? The previous logic is, okay, we can do some sample weighting, and then we can find out the independent variables, and from the independent variables, okay, we can find out the causal variables. And the hypothesis is that the causal variables are stable, so we can make a stable prediction. We think that maybe there is a more direct logic. We do some sample weighting, then we can find all the independent variables. And the independent variables can directly lead to stable prediction results. That's the another way to think about this problem. We want to think about, okay, the stable learning problem from the learning end. So why today's learning model cannot produce stable performance in different distributions? So here, just to show you an example, here is Px is the training distribution is a Gaussian. In most of today's model, actually, we just optimize the overall loss in this kind of distribution. Then we will get the result, of course, is that for the point in this region, you have a small prediction error, right? And for the points in this region, you have large error because we regard them as quantum points. If we train a model in this way, just think about that the distribution change into this, then actually the previously quantum points is not the quantum points anymore here, but as the mainstream points. But the model cannot guarantee stable performance in this kind of different distributions. So the problem is, how can we guarantee a stable performance? If we can just learn a predictive model which can achieve uniformly small error on any data point, then no matter how your distribution change, we can guarantee stable performance. Here we just consider a very simple linear regression setting with some specification bias. So here you can see that y is generated by beta x plus bx plus the noise. So the bx here is a bias term and is bounded by delta. So that, okay, the generation of y is still dominated by the beta, not dominated by bx. In this kind of model, if we can accurately estimate the beta bar with a property that bx is uniform small for all x, then we can achieve the stable learning. If you just want to make a stable prediction, then the most safe way is just to use beta bar, because the bx actually is a bias term, and bias term cannot be correctly estimated anyway. Then we just do some theoretical analysis here, and we found that, okay, the estimation error between beta hat and the beta bar, here are the upper bound we proved. You can see that the gamma square is the smallest eigenvalue of the centered covariance matrix of X. And when the gamma square is very small, that means, okay, the bias term will go to infinity when there exists a perfect collinearity. So we can actually use eigenvalues to indicate that the degree of collinearity in the input variables. When the smallest eigenvalue is very, very small, that means, okay, there exists a very strong collinearity in the input variables. So when there are perfect collinearity in the input variables, you can see that, okay, the estimation error will go to infinity. So in this sense, okay, that means collinearity actually is a main cause of the instability in this kind of problem setting. Then we just do two examples. So here we just assume we have a design matrix X, and X is composed by two variables, X1 and X2, and they are generated from a multivariate normal distribution. The sigma here is the covariance in its form, and the rho you can regard it as a controller to control the collinearity between the variables. When the rho is very large, that means there are very strong collinearity in the input variables here. We further induce the bias term and make it related to the collinearity. You can simply think that the bias term actually is very sensitive to the collinearity. Here you can see that here we just tune the values of the rho to get different smallest eigenvalues from 0.9 to 0.1. That means, okay, an increase the collinearity, and the stronger collinearity will bring higher estimation error. You can see the average bar here goes higher and higher. And based on this, we can change the distribution of the training distribution, and they will have a variance here, and you can see that the estimation error will be inflated right, and when very significantly when the collinearity is very strong. So all of this actually can demonstrate the collinearity actually is a key factor that make a learning model to be unstable. The key idea here is to learn a new set of sample weight which decorrelate the input variables and also increase the smallest eigenvalue. If we just do this kind of simple sample weights, we can just use a weighted least square estimation, which actually is equivalent to another setting that is we just use a new distribution d tilde, and in the new distribution we just do the normal least square, so that's the equivalent. The problem is how can we find out an oracle distribution, the d tilde here, which holds a desired property that all of the variables are decorrelated, or at least will reduce their collinearity or increase the smallest eigenvalue. We propose a very simple method here. That is, this is an original design matrix, and this is a target design matrix. We hope that in the target design matrix, all of the variables, they have very weak collinearity or even no collinearity there. So we just do this, that, okay, we can treat the different columns independently, and we perform random resembling, which can guarantee the different variables can be decorrelated, and then we can obtain column decorrelated design matrix x tilde here with the same marginal distribution as before, as the original design matrix. Then we can just use the density ratio estimation to get the WX. In simulation study, we vary the collinearity in the training data. This is an estimation error we compared with ordinary least square, the U lasso, I lasso, and many baselines, and you can see that we can significantly reduce the estimation error here. And if you just use this kind of estimated beta to do predictions, you will see a relatively stable performance compared to other baselines. And you just change the distributions and calculate the average performance and the variance between different distributions. You can find that our method has smaller average error, and also the variance is very small. We just use this for some other regression tasks in real data, and you can also observe the difference. And also in some classification tasks, you can also observe similar patterns. Such reweighting scheme can effectively reduce the bias brought by misspecification term, but increase the estimation variance in return. In situations where we have not enough samples relative to the dimensions of variables, the over-aggressive strategy that removing all the dependencies among variables would greatly shrink the effective sample size and inflate variance to an unacceptable level. To remedy such deficiency, we propose a more realistic model setting. We assume there exists a decomposition of variables x equals s and v, which represent stable variables and unstable variables respectively. The outcome y is determined by the stable variables s, regardless of y. The key reason of instability is there may exist spurious correlation between unstable variable v and outcome y due to the selection bias or the unobserved confounder. More formally, we can derive the closed form solution of traditional least squares operator on the linear models with misspecification error. Through the previous research, we could find that the estimation error of unstable variables v may influence by the covariance between stable variable and the unstable variable. If we assume the zero means of all the variables, such correlation is unstable and likely to change across environments. Removing such correlation helps to improve the estimation accuracy and further stabilize the model performance. At the contrary, removing the correlation between stable variables, which is unlikely to change, helps the model in a limited way and further causes the over-reduced sample size. So the question is how to remove the sparse correlation directly and efficiently. It is quite a common knowledge that through a sample weighting on predictor variables, basically unsupervised method could not directly identify which variables belong to stable part and which one belongs to unstable part. So here comes to two most important assumptions in this work: heterogeneity and modularity. The heterogeneity means we have multiple training data sources which corresponds to different data distributions. Note that a similar research area, domain generalization, also assumes the availability of multiple training sources. However, in this work, we only assume the unlabeled heterogeneous data compared with fully labeled data in domain generalization. We think it is a more realistic and in real scenarios. The modularity means the variables do not act as individuals. There exists inner structures among all the variables. Specifically, modularity reads as following assumption: the variable could be partitioned into k distinct groups. Distributions among the same group remains stable across different environments, and vice versa. Take the following image as an example. The joint distribution of cows, air, and nose, or more consistently, the correlation between air and nose remains stable across changing domains. They should belong to the same group. However, the correlation between grass and cloud could change arbitrarily. Therefore, they should belong to different groups. So an intuitive question is, could we leverage the heterogeneous data sources to recover such inner structure in a way like clustering? Following such concept, we propose to partition variables into different groups by stable correlation clustering of two. Specifically, we define the dissimilarity of two variables as the variance of their Pearson correlation coefficients across different environments. As an approximation, such metric could reflect how the joint distribution of two variables changes in the multiple environments. The smaller dissimilarity indicates a larger possibility that these two variables are in the same cluster. Then we can incorporate the clustering results into the variable decorrelation framework through learning a new set of sample weights. We could remove the correlation between variables from different clusters. We first generate some synthetic data with non-generation process to simulate sparse correlation. For each sample, we select it with a non-uniform probability affected by a bias rate R, which R greater than 1 indicates positive correlation between V and Y, and R less than -1 indicates negative correlation. By manipulating the value of bias rate, we can generate different environments with different correlations. Here are the results of simulation data. We can find that the baseline methods suffer from unstable performance across different test environments, and the performance deteriorates as the discrepancy between training and test data getting larger. And DVD can improve estimation error on training data and relieve the variance inflation compared with the sample reweighting baseline. DWR, leading to its more stable performance across different environments. We vary the parameters in generation process and test our method in several different settings. In most cases, DVD can outperform the baselines. Furthermore, we compare the effective sample size of two reweighting methods. We can find that as the variable dimension grows, the effective sample size shrink quickly for baselines, while our method maintains a relatively larger sample size. We also conduct real data experiments on a housed cell price prediction task. We simulate environments via the period of house built years. In training process, we only use the first 2 decades of the 20th century and test the model on all the periods. The results indicate that our method can achieve better performance when the test distribution deviates larger from the training distribution. So far, we have formulated the stable learning as a general learning problem and discussed it from two different perspectives. Now we want to move a little bit further and talk about some concrete applications in which the stable learning techniques might help. First of all, as we know, graph is a general and powerful representation to describe the rich relationships among kinds of entities due to the relational patterns underlying it in its structure. The varied relationships signify the change graph structure over the same entities in different environments, reminding us to pay attention to the stability of performance for these graphs across environments. Let's take a look on a real example. What goes best with fried chicken? If you ask an American, he may choose Coke without hesitation. However, if you recommend this diet to a Korean, he may refuse it and says fried chicken and beer are the perfect match. People from different countries prefer different correlations between chickens, Coke, and beer. And similar phenomena is quite common in daily life. Our target issue can be formalized as the data selection bias problem of graph generation. Supposing two graphs are constructed in two independent processes from a data source. However, the first time we sample raw data from environment 1 marked with green box, while only the data in blue box are collected in environment 2 for the second time. The correlations implied in two environments are apparently different. And the connection between A and B in green box is much stronger than that in blue box. As a result, the build graph is consistent with itself environment, but they cannot be applied to the other one, not to mention the whole data source. In a word, the data collection process of graph generation is full of a non-sample selection bias, leading to biased correlations among entities and unstable performance of graph across heterogeneous environments. But to correct the bias structure is quite challenging. First, the input data used to construct the graph is usually sparse. The complex correlations underlying in structure are high-ordered and potentially nonlinear. And the scale of graph could be very large. Anyway, the single environment actually loses some information. What if multiple environments with different selection bias are provided? Can we leverage them to achieve a stable graph that is generalized enough to arbitrary distribution? However, directly eliminating bias on the original graph structure space, like for example, adjacency matrix, is quite hard. An alternative plan is to find a transform space from graph structure by function h. Firstly, then in new space, we can use a function f of low complexity to debias in multiple environments and obtain a stable one. Finally, we can find a stable graph structure corresponding to it without extra cost. Let's consider about how the sparse raw data is generated. Assuming a data sample is represented by a set consisting of several elements, like products in a shopping basket in recommendation system. Starting from an empty set, a new element is selected into the current set one by one until arriving the steady state when the set won't expand by adding elements. Like how we choose items into shopping basket, as the selection process is according to the existing elements in the set. That is to say that the set generation process is guided by a series of conditional probability which would be encoded in graph structure. One thing worth to be noted is that the probability of adding into an empty set refers to the prior preference of data selection, like that the female users are more concerned with the skincare products than the males. Obviously, the prior distribution is not contained in graph, but its bias can affect the learning of stable structure. Because the graph structure underlies the mechanism of set generation, we can use a function h to transform it into a conditional probability space over we can transform it to a conditional probability space over all the elements given arbitrarily existing set. Now we consider this transform space as an ideal space for us to indirectly correct the graph structure. For example, after finishing transformation, the green and blue density curve represent generative probability in the two environments respectively. The mean curve of the purple one is certainly more general than the other two for both environments. This mean function is simple and also effective. And if we have mean pooled all the generative probability, the only thing to do next is to find a stable graph so that it can embed the balanced generative mechanism. For the purpose, we design a stable graph learning framework. In the first phase, we fix the graphs constructed in each environment and update the parameters in graph convolutional neural network and element-wise variational autoencoder, enabling the two modules with the capability to generate the set data in the corresponding environment from the constructed graph. The set vector is the output of a mean pooling operation of the element embedding matrix learned by GCN from constructed graph and the real data set. Each element embedding concatenates with the sample latent vector and is fed into the decoder separately. Combining all the decoder's output together, we obtain the conditional probability space over all elements after a softmax layer. By maximizing likelihood of observed data, we learn the probability of generating a set in every single environment. In the second phase, we fix the parameter in GCN and EVAE and refine the graph structure to make the probability of generating a set equals to the average probability of generating a set over all the environments. Assuming the environments are randomly selected with different selection bias, the resulted graph structure contains less bias than every single environment, and consequentially possesses the superiority in producing stable performance across different environments in subsequent tasks. We conduct experiments on both simulation data and real data sets to bring about distribution shift in two data environments. We make biased weighted random walk to simulate the generation of set data. Compared to traditional weighted random walk, we cluster nodes into different groups in different environments for correlation bias and use function Q to increase the probability of moving the same group when random walk. In addition to the first order and second order bias controlled by Q1 and Q2, we also introduce the zero order bias represented by Q0 that simulates the prior preference of data selection. For example, as we mentioned above, the female users are more concerned with the skincare products than the males. For evaluation, we use the set prediction task based on the learned node embeddings to test the stability of graph structure across 11 different data distributions. So for the baselines, G1 and G2 are graphs from single environments. GA is average graphs from single environment, and GC is generated from the union of data in all environments. The general performance of the proposed method is quite convincing at each setting. So for the more detailed analysis, the performance of the graph built on single environment rapidly declines as the data proportion from another environment increases. The performance of GS is much more stable and achieves higher mean accuracy than all the baselines in almost all experiments. It is because GS directly learns the less biased, high-ordered, and also nonlinear correlations among the nodes at the level of generation probability from two environments. For real applications, we choose the commodity recommendation on e-commerce platform of Alibaba. Specifically, we study the behavior prediction tasks when the exposure bias or the user group bias happens. The former is the online system prefer to recommend popular items, causing the unpopular items and the new items to get harder to obtain exposure. Also, for example, the cold start problem. And the latter refers to the difference of group proportion. Like the simulation experiments, we divide a purchasing history into two environments according to commodity popularity or user gender. from the results, we can observe that the behaviors in different environments have different prediction difficulties. For example, the relation between popular items are easier to be predicted because they are apt to be associated by recommendation. For example, women tend to purchase all the related goods together at once. Also, the stable commodity network, GS, can balance the correlation in both environments and reach the highest mean prediction rate more stably. For a new research direction like stable learning, benchmark datasets which could provide a fair comparison ground for competing approaches are very crucial. Take image classification, a prominent learning task, as an example. The emergence of high quality and large benchmark like ImageNet has greatly accelerated the development of visual learning. For traditional learning tasks which based on the IID hypothesis, researchers can easily find handy datasets. While in stable learning, where we assume an agnostic and changing test distribution, the existing benchmarks could not well support such a research purpose. We just calculate the metric for image classification. We just calculate the metric that is called NI and as the non-ID index. So it's for each category, we just measure the difference between the training set and the testing set. So how different is the training and testing data set? And then we do a normalization here. And you will find that, okay, actually in the ImageNet, different categories, they have different NI index. And if you use the same model to do classification, in different categories, you will find phenomenon in this figure. In this figure, that the bar means the NI value in this category, and the yellow curve means the error rate. Okay, so we will see that the error rate actually is perfectly correlated with NI. That means, okay, in the category that there have a higher degree of non-ID, then the existing models actually cannot work well. That's our finding here. So the problem is the existing data set, including Pascal, VOC, the ImageNet, MS Coco, you can calculate NI for categories, and then you will find all of these data set. If you just do some random sampling, the NI is quite small, and moreover, the NI is uncontrollable. So if you want to simulate even more challenging distribution change, actually this kind of data set cannot provide you a flexible way to modify NI value. So we think that a data set which can support this kind of distribution change, image classification, is highly demanded. Here we just construct a Nico dataset, and in this dataset we provide the object label, and also we provide some contextual label. For example, the object label is dog, and the contextual label is on grass or in the water. And this is the structure of Nico. So in total we have 2 superclass, and each superclass we have 10 classes, and in each classes we provide extra 10 contexts so that we can generate diverse, meaningful, and overlapping contexture here. The data size is for each superclass we have 10,000 images, and for each class we have about 1,000 images. Here is a snapshot of the whole data set. If you see that for each category we will provide different contexts, like at home or on beach, something like that. And then based on this kind of data set, we can control the NI index. Next, we will introduce how to control NI value on our Nico data set for non-ID image classification. By controlling the number of contexts and the number of samples in each context, we propose 3 ways to control the NI value, including minimum bias, proportional bias, and compositional bias. Here we introduce the minimum bias method. In this setting, we randomly sample 8,000 samples for training and 2,000 samples for testing in each superclass, and calculate their average NI values as follows. Since the training and testing are randomly sampled, there should be a nearly ID scenario. But we find that the average NI for animal class is 3.85 and 3.2 for vehicle superclass. This is because of the rich contextual information. In our dataset, each image has not only a class label but also a contextual label. By comparing with the ImageNet dataset, we can find our Nico dataset is more biased, or with higher average NI value. Next, we will introduce how to control the NI value by proportional bias. In this setting, for each class, we use all contexts for both training and testing, but the percentage of the number of each context is different in the training and testing dataset. In both training and testing, we pick one context as dominant context and other contexts as minor contexts, and they have the same percentage. For example, in the dog class, we chose the context at home as the dominant context if its percentage in our dataset is 55%. Then the percentage of each other context is 5%. Here we define the dominant ratio of a dataset as the percentage of dominant context over the percentage of the minor context. In this example, its dominant ratio is 55/5 and equals 11. In this way, we can generate the NID scenario by changing dominant ratio in training and testing data set. And we have demonstrated that the NID value, if we set the dominant ratio on testing dataset as 1, but varying different dominant ratio on training data. From the result, we find that as increasing of the dominant ratio on training data, the NI value become bigger and bigger. Hence, we can control the NI value in our dataset by changing the dominant ratio on training and testing data. The third way to control NI is in our Nico dataset is by compositional bias. The compositional bias is induced by the observed context different between training and testing, including two settings. One is moderate setting, where the observed context between training and testing has overlap. Specifically, in testing data, we observed all 10 contexts for each class, but only observe a part of context in the training. By changing the context we observed in the training, we can control the NI value between training and testing. And from our experimental result, we find that as decreasing of the number of observed contexts in training data, the NI value become bigger and bigger. Another setting is a radical setting, where the observed context between training and testing has no overlap. Specifically, we let the observed context in training is the first 5 contexts and the last 5 contexts are the observed in testing. Moreover, we involved the proportional bias on training data in this setting. From the results, we find that the NI value in this setting is has been increased as the increasing of the dominant ratio in the training data. Between these two settings, we find that the lowest NI value in the radical setting is bigger than the largest one in the moderate setting. Therefore, with compositional bias, we could control the NI value in our Nico dataset, and we can make larger NI by combining the compositional bias and the proportional bias methods. Here we give a summary of our NID our datasets. To control the NI value on our datasets, we propose 3 ways, including minimum bias, proportional bias, and compositional bias. And we could demonstrate the range of the NI value in this figure. From this figure, we find that the NI value in ImageNet is too small and cannot be controlled, since the ImageNet is not designed for non-ID image classification. Based on our Nico dataset, I would propose 3 ways can control the NI value and generate larger NI value than the ImageNet. And as we change it in a controllable way, we can make the NI value increase from small to large. By controlling the NI values in data, we can generate different settings for non-ID image classification. For the preliminary comparison of different stable learning algorithms, we also propose a simple but competitive baseline, which incorporates the notion of global balancing in the scenario of convolutional neural network. The experimental results on Nico have demonstrated that under the changing distribution, our method could achieve better generalization ability compared with vanilla CNN and mainstream techniques against overfitting like batch normalization. Finally, we will give a quick conclusion of today's tutorial. Stable learning cares about not only the prediction accuracy, but also the prediction stability across different distributions. And we find that causality somehow shed light on the intrinsic mechanism of stable learning and could provide a firm soil for the upcoming research. But how to marry causality with predict modeling effectively and further connected it to the representation learning is still an open problem. So that's all of today's tutorial. Thanks for listening.